Hi, this is Dr. Anthony Revis with SVSU, Gen Chem 111, Chapter 10, Lecture 2. That's Lecture 2 of Chapter 10 on Intermolecular Forces. In this chapter, we will look at intermolecular forces, properties of liquids, phase transitions, phase diagrams, the solid state of matter, and we will also look at lattice structure in crystalline solids. When we examine these topics, we will look at them, but not necessarily in this order. Also, Chapter 10 is taught as a survey overview of the topics than an in-depth discussion. So let's get started with Chapter 10, Intermolecular Forces. Let's start this lecture with a brief review of what we mean when we talk about intermolecular forces. Intermolecular forces are attractive forces between molecules. They are the sum of all the forces between the two neighboring molecules. Whatever those forces are, they come together, and that's what we call intermolecular forces. Okay? Now, there are four intermolecular forces that we talk about in Gen Chem. One, ionic forces, or interaction between charged atoms. Two, hydrogen bonding occurs in molecules. Three, van der Waals, or dipole-dipole interactions. Four, van der Waals or dispersion forces, which we call London forces. These are the forces that we talk about. Okay? In this chapter, we will be talking a lot about phases, and therefore, for example purposes, we will talk quite a bit about hydrogen bonding because we will use water as our example. Okay? So now, the phase in which a substance exists depends on the relative extent of the intermolecular forces and the kinetic energies of the molecules. And we note in our diagram here, increase in kinetic energy goes with temperature, and it moves from solid to gas. And we'll only talk about the solid, liquid, and gas phase. We note that the increase in intermolecular forces move from the right to the left side. It's important to keep this in mind as we talk about intermolecular forces and we start to talk about phases. Now, we began this lecture by pointing out to you that phases, or the phase a material is in, is a result of the intermolecular forces at play. So when these intermolecular forces are at play, the material will find itself landing in a particular phase. We show you the phases again for solid, liquid, gas. We note that increase in molecular forces go to the left, go toward the solid. Increase in kinetic energy go to the right, towards the gas. So, what's a phase? A phase is a homogeneous part of the system in contact with other parts of the system by separation from them by a well-defined barrier. In other words, they're in contact, but they are separated by a well-defined barrier. In other words, one's a solid, one's a liquid, one's a gas. So they're separated by this barrier of being a solid, a liquid, a gas. Okay? And it's very clear. You can define a solid, you can see the solid, you know the properties of the solid. And those properties are different from the properties of a liquid. And those properties of the liquid are different from the properties of a gas. Okay? And so that's what a phase is. It's like a liquid, solid, gas. Okay? What phase is it in? Okay? So, we show you some characteristic properties of gas, liquids, and solids. Properties of these phases. When we look at the gas phase, okay, it assumes the volume and shape of its container. These are principles that you already know and consider this to be a review of them. And we're reviewing them because we now understand that the reason it has this phase or exists in this phase is because of its intermolecular forces. We know this gas has a low density, it's compressible, and it has very free motion. These properties or characteristics are consistent with the intermolecular forces for this molecule, H2O, in the gas phase. And we're using water as the example. Okay? The liquid has a definite volume but assumes the shape of whatever the container is. Density is higher. It's only slightly compressible. And its motion of the molecules slides past one another freely. It doesn't have quite the free motion as the gas. And then we have the solid phase. Solid phase has a definite volume and shape. Solids typically have a high density except for water. And you know why water doesn't have that, right? Yes, hydrogen bonding doesn't allow it to compress as much as other liquids do when it's freezing. The hydrogen bonding interferes with that and makes its density lower because it has a higher volume. But water is the exception. In general, the solids will have higher density. It is virtually incompressible. You don't compress the solids. And it only vibrates from its fixed position. In other words, it doesn't have a lot of activity. It doesn't have a high kinetic energy. Okay? So these are the phases, and these are the characteristics of these phases. These phases exist because of their intermolecular forces. Now, again, note that a phase is defined by boundaries. They have clear boundaries that you can define. That brings us to a discussion about phase diagrams, and we will use water as our first example. A phase diagram summarizes the conditions at which a substance exists in the solid phase, the liquid phase, or the gas phase. We look at the diagram, and we like to bring your attention to first where they all three come together: solid, liquid, and vapor or gas. And that point is called the triple point. That's where we have all three existing at the same time. It's one of those wonderful features about solid, liquid, and gas phase diagrams. If we go to the left and up in pressure, we are at the solid phase. If we go to the right in temperature, we are in the liquid phase. And if we continue to go up in pressure and temperature, we are in the vapor or gas phase. So this is what the phase diagram for water looks like. It helps us to understand where we can acquire a particular phase based upon temperature and pressure. Okay? So it's important to note that pressure and temperature are critical variables for determining the phase of water and other substances. And when we say water, we mean H2O. Solid water, liquid water, vapor water. H2O. Okay? Now, we look at the energy diagram to the right, which shows how these phases transition. And we are aware of this because we've already done this type of study when we studied thermodynamics. So if we look at these thermodynamic factors, what we find for H2O is that as a solid, it can be sublimed directly to the gas phase. And you can see that on the phase diagram. For example, if you take the pressure below 0.006 and take it even lower, we can go directly from solid, from the purple colored phase, directly to the orange colored phase, which is the vapor phase. So what this diagram helps us to see is what it takes to go from one phase to the other. So sublimation, delta H of sublimation, we can do that and go directly to the gas phase. There's also delta H of fusion, the heat of fusion, can take us from the solid to the liquid, and then the vaporization, heat of vaporization can go from the liquid to the gas. And again, these are thermodynamic properties that you are now aware of, okay, and that you've seen before. So we can go from solid to liquid, liquid to gas, solid to gas. We can use these thermodynamic factors to determine the heat of sublimation. Or you can take the heat of sublimation, subtract out of one of these, and get the other. Okay? So, just to take a look at this and explain it one step further. The effect of increase in pressure on melting point of ice and the boiling point of water, it can be altered. We can change any of these properties depending on what phase we want to get, and that's the point of this slide. Okay? So, we want to decrease melting point, we can shift it about. We want to increase the boiling point, we can shift it. So if we take a look at this phase diagram, we can set conditions of temperature and pressure to achieve either the vapor, the liquid, or the solid state. We can also take a look at a phase diagram for carbon dioxide. If we look at its phase diagram, we also have a triple point for it. We have solid, liquid, vapor. However, the temperature and pressure requirements to go across these phases or to reach a particular phase will be different. In the case of carbon dioxide, we have carbon dioxide solid, goes directly to carbon dioxide gas, and that's why the entertainers are able to use it on stage for their smoke effects, because carbon dioxide would go directly from solid to the gaseous state under very mild conditions. So that's why it's used by the entertainers for smoke. Okay? So that is a phase diagram for carbon dioxide. So, you got that? So now, let's talk a bit further then about intermolecular forces and phase transitions. And let's look specifically at vaporization and condensation. So first of all, what is vaporization? Vaporization of a liquid is a phase transition. In other words, you're going from one phase to another. In this case, you're going from liquid to gas or from liquid to vapor. So vaporization of a liquid is a phase transition from a liquid phase to vapor. Vaporization happens either as evaporation or boiling. Those are the two ways we express vaporization, either evaporation or boiling. Now, evaporation is a surface phenomenon. In other words, it happens at the surface of the liquid. And boiling is a bulk phenomenon. In other words, it happens from within the bulk. So when we think of a surface phenomena, that means we are essentially removing those top layers of the water molecules out of the water phase, one monolayer, if you will, or one small layer at a time from the top. In the case of boiling, however, we're actually applying energy to the bulk substance such that the molecules in the middle of the liquid phase are as affected as the atoms or molecules on the top. Okay? Now, the rate of evaporation is proportional to surface area. So greater surface area means faster evaporation. And that is a concept you want to hold on to. If we take, for example, a glass of water and we sit it in the sun for it to evaporate, it will evaporate slower than if we take that same glass of water and pour it out in a baking pan. We are exposing more surface area, therefore evaporation happens at a higher rate. So keep in mind then that evaporation is proportional to the surface area. And there are many different ways to do the calculation depending on which industry you're in. Each industry has its own way of doing those calculations. But in all of those calculations and in all of the ways we think about it, surface area is part of the consideration. Okay? Now, the change from gas phase to the liquid is called condensation. In other words, now you're going from the gas, highly energetic state, loss of atoms, and now you're taking that same concentration atoms and you're bringing them closer together. You are condensing them. When the rate of condensation becomes equal to the rate of vaporization, the vapor inside of a container, if it's inside a container, then that rate is said to be in dynamic equilibrium because it is not a static situation. Keep in mind, many of the models that are used to discuss this involve closed container considerations. Okay? So when we have this occurring, it is called a dynamic equilibrium. The chemical identity of the molecules in the liquid determine the types of strengths of the intermolecular attractions, and that's a key principle we want to make sure we get across. That the types of intermolecular forces that are at play depend on the type of molecules. For example, if it's alcohol, which has OH functionality, it will involve hydrogen bonding. If it's a hydrocarbon where there are no OHs, then it would involve London or dispersion forces. Okay? So you want to keep that in mind. And here are two key principles to take home from this. Relatively strong intermolecular attractions will impede vaporization. So if the intermolecular forces are really strong, then vaporization will require more energy to occur. Okay? In other words, those attractive forces are impeding its progress towards evaporating, towards separating one molecule from the other and moving into the gas phase. All right? Principle number 2 that we get from this: weak intermolecular attractions yield relatively high vapor pressures. Okay? So if they're weak, the vapor pressure is high because there are lots of those atoms in the gas phase at that temperature. Now, you want to note, temperature is one of the variables that we consider when we talk about vaporization, condensation, dynamic equilibrium. When we talk about strong and weak forces, we must also consider the temperature factor. Okay? But overall, weak intermolecular forces have high vapor pressure because they readily go into the gas phase. That brings us to the concept of boiling point. When the vapor pressure increases enough such that it equals the external atmospheric pressure, the liquid reaches its boiling point. It's that point at which it now wants to move over from the liquid phase into the gas phase. And it will start that process at that temperature and at that pressure. The boiling point of a liquid is the temperature at which its equilibrium vapor pressure is equal to the pressure exerted on the liquid by the gaseous surroundings. In other words, there is pressure being exerted on the liquid. And when that pressure of the liquid has matched the pressure being exerted against it, then it boils. It escapes its liquid phase and it goes into the gas phase with the rest of the gas molecules that are pushing against it. The liquid then escapes into the surrounding, whatever the surrounding is. Okay? And this is important. The kinetic energy of the gas increases as it escapes into the gas phase. Okay? So the kinetic energy increases. In other words, the molecules are running around much faster. Okay? They're bombarding things much faster. They're colliding faster. They're moving much at a higher rate, or they're moving with more energy once it reaches that temperature. Okay? So that's vaporization, condensation, and boiling point. So what does that mean for boiling point? Again, the boiling point of a liquid is the temperature at which its equilibrium vapor pressure is equal to the pressure exerted on the liquid by its gaseous surroundings. When a liquid vaporizes, it escapes into the surroundings, into the environment. We show you here a graph which shows pressure versus temperature. These are the important factors when we think about vapor pressure, when we think about boiling points. Okay? Considering the definition of boiling point, these curves, okay, may be seen as depicting the dependence of a liquid's boiling point on the surrounding pressure. Okay? And that's important. That's why certain liquids boil at different boiling points depending on where they are in the U.S. In Denver, it's a different boiling point than it is when you're in Michigan or in some valley state, because there is a different amount of pressure being exerted on the liquid. So taking a quick look at this diagram, just want to show you that ethyl ether has a higher vapor pressure, lower boiling point than ethyl alcohol. One of the key differences there being the OH versus an ether. So the hydrogen bonding in alcohol, ethyl ether, affects its intermolecular forces. And then water has even more OH impact, so that its boiling point is even higher. And then we go to ethylene glycol, and there are several reasons for ethylene glycol. Again, we have ethylene glycol, which is OH rich, if you will. So it has an even higher boiling point, meaning a lower vapor pressure. There are fewer molecules of it in the vapor phase, all things being equal. So we have that. Now, what can we do with this information? We can use this information to determine how much energy is required for a material to enter the vapor phase, or at what temperature or what pressure. And we do that quantitatively by what's called a Clapeyron equation. Okay? So, the quantitative relationship between a substance vapor pressure and its temperature is described by this Clapeyron equation. And we're not going to go into detail of the derivation in this particular chapter, but suffice to say, you see the equation, P equals AE raised to the delta H of vaporization over the constant, the gas constant, times the temperature, and the temperature would be in Kelvin. And this is the equation, but the most useful form of this equation is when we take the log so we can get a straight line. And when we take the log of this and we rearrange this equation, again, which we won't go into detail, it's something that by now you're familiar with how to do these types of things, but essentially we rearrange the equation and we get the final form that we use most often in these types of calculations involving enthalpy of vaporization. Okay? And so we have the enthalpy of vaporization equation here. And you see the factors. A, by the way, is a constant, and it depends on which material. For example, A for ethyl ether, ethyl alcohol, water, and ethylene glycol. They will have their own unique A constant. It corrects for that particular material and for the chemistry or the configuration of that particular molecule or substance. Okay? And note that vaporization is an endothermic process, and you intuitively know that because you know that melting ice requires heat in. So it's an endothermic process. The ice must absorb some energy, some heat. In this case, it's your stove top or your butane burner to melt it, and you get it to melt. So keep in mind, vaporization is an endothermic process. So here's an example of using the Clausius-Clapeyron equation to carry out calculations. We will not go into any detail in this lecture, but we'd like for you to take a look at this and work through the problems. Essentially, we have isooctane, has an octane rating of 100. It's used as one of the standards for octane rating in gasoline. Here's the problem. At 34 degrees C, the vapor pressure of isooctane is shown here at 10 kilopascals. At 98.8 degrees C, we note already we have to change degree Kelvin. We keep that in mind already. And we have to make sure we choose an R that matches the units in the problem. So we use this information to estimate the enthalpy of vaporization of isooctane, and that's pretty important to how it's stored and how it's used. So we use the Clausius-Clapeyron equation. We take this equation and we painstakingly rearrange it using the rules of math. Then we put in all the values. Again, we will not go through each step by step, but it's straightforward. Choose the variables, put them in. Temperature must be in K. R must match the units that are part of the problem. So make sure you choose the proper R. You do that, we get a value of 33.8 kilojoules per each mole. And that's important to know. Okay? So these are the things you want to do when you work these problems. Otherwise, they're straightforward. At this point in your chemistry career, you know how to rearrange equations and how to plug them in. We just show you again another example of how we can use this to estimate the temperature. In this case, we have benzene, which has a boiling point of 80.1 degrees C. So you're thinking Kelvin. Keep in mind, it's not degrees Kelvin, it's Kelvin. So you're thinking Kelvin. You note that you have the enthalpy of vaporization already given in kilojoules per mole. You have the pressure given in 83.4 kilopascals. This is a straightforward substitute in the values. Be sure that your temperatures are in Kelvin. Note that you have your T2 versus your T1. Choose T2 when you rearrange the equation. You plug it in and you get 346.9 K, not degrees K, but K, or 73.8 degrees C. So that is how we would use the Clausius-Clapeyron equation to determine temperature or enthalpy or pressure or whatever variable we're interested in at the time. Now, we've talked about condensation and vaporization. Let's talk now about melting and freezing. Okay? Because that is another point of transition from one phase to another. From solid to liquid or liquid to solid. Okay? So, here it is. When a solid is heated, the average energy of its atoms increases with the heating. That's what happens. You heat it, it gets more energy, the kinetic energy increases. When the energy is large enough to partially overcome the forces holding the solid, not completely, but it starts to overcome them, it transitions into the liquid state until all of the solid is melted. In other words, it makes its transition when all of the solid is melted, then it starts to do whatever else it's going to do. But all of the solid gets melted, then it moves on. It only moves on when it's all melted. Only after all the solid has been melted will continued heating increase the temperature of the formed liquid. So the temperature is going to sit there until it's all melted. Okay? In a solid and liquid at equilibrium, the reciprocal process of melting and freezing occur at equal rates. So you're either on the melting side or the freezing side, and they occur at equal rates. That's how it is. One's positive, one's negative. One goes right, the other goes left. And the quantity of solid and liquid, therefore, remain constant. The quantity of solid and liquid are the same. If you start with 1 gram of ice, you'll get 1 gram of liquid, assuming you don't lose any or drop it somewhere. Okay? The temperature at which the solid and liquid phase of a given substance are in equilibrium is called its melting point. The melting point is where they hit it, where you get solid liquid, and if you watch it in a melting point apparatus, you see it happening. You go from solid and instantly you go to the liquid. So you reach the melting point of the solid or the freezing point of the liquid. So you have the melting point of the solid or the freezing point of the liquid, and you intuitively know these things. Okay. Now, the enthalpy of fusion, that's melting to liquid or liquid to melting, and the melting point of the crystalline solid depend on the strength of the attractive forces between its units in the crystal. And you intuitively know that the intermolecular forces matter in these matters. Okay? Molecules with weak attractive forces form crystals with low melting point. So they have weak forces, it has a low melting point. Crystal consisting of particles with strong attractive forces melt at higher temperatures. So you have higher temperature melting, that means it has stronger intermolecular forces. It has lower melting point, that means it has weak intermolecular forces. Again, these are concepts that by now you intuitively know. We're just trying to help put them in a form of definitions to understand intermolecular forces and phase transitions. So here's what comes out of this. Watch this. The heat required to change 1 mole of a substance from a solid state to the liquid state is the enthalpy of fusion, delta H fusion. Fusion, melting, is the endothermic process. When something melts, it is endothermic. The reciprocal process, freezing, is exothermic process. In other words, we have positive fusion, endothermic, negative fusion, exothermic, and you know that endothermic carries a positive value and exothermic carries a negative value. Okay? And that's what's happening. When it melts, it is endothermic. When it freezes, it is exothermic. It releases the energy. So let me finish this by walking through this diagram shown here at a pretty good pace. You'd be wise to go back and take time and walk through this a bit slower. We show you here an energy diagram for water. This could be any other liquid, but water is a good standard to teach the concept from. So if we have water going from a negative temperature starting in region A to a positive and high temperature in E, we have transitions that we go through. We essentially have a solid that must be converted to a liquid that must be converted to a gas. You've looked at these concepts in earlier chapters in this course. So, what we have happening is, starting in region A, we start at a negative temperature, less than 0. In the case of water, we know 0 is a transition point. So, we start at negative temperature and we heat up to 0. Once we reach 0, that solid starts to melt, and it melts until all is melted at 0, and then the heat or energy applied will allow it to rise until it hits 100 degrees C for water, whatever its boiling point is, or for the liquid. Once it hits that point, it will now stay there, and it will stay at 100 degrees until all those molecules of water have decided to enter the gas phase, and then the temperature will rise. So essentially, when we have a transition from a solid to a liquid or liquid to gas, all of the molecules must enter that state, that transition state, before the heat being applied can be used to drive it further at the state it is now in. Okay? So we see where we start melting, and we see where all the solids melted. We see where we start evaporation, and all of it's evaporated. And this is why we use these equations for calculating delta H and heat energy. Or we could calculate T or some other factor. But when we want to know the heat equation for each of these phases, this is why the equations are different, because there is a different phenomena that's occurring at each of these positions in this transition from ice at a negative temperature to gas at a higher temperature. So if it involves a temperature change, we use the temperature change equation. If there's no temperature change, meaning there's just a phase transition or a state change, we use the equation where we have the heat of fusion. Okay? And if, again, we are back to where a temperature change, we use the equation for temperature change, which involves the specific heat, and so on and so forth. All right? So this is what it looks like when we do these transitions. What's the summary of this? What we know then is that intermolecular forces are stronger to the left. We know that kinetic energy is stronger to the right. We know that endothermic processes move from left to right, and exothermic processes move from right to left. Okay? That's what we learned from this. And so now, another way to draw this is to take a look at the number of molecules that are in the gas phase or that enter the gas phase. Okay? So we take a look at this diagram here, which shows the number of molecules versus the kinetic energy. And what happens is we reach this point where the kinetic energy has its minimal energy to escape from the liquid phase into the gas phase. That's what we see in the larger diagram. So we have number of molecules versus kinetic energy. And what happens, these large curves, where say low temperature, we have that curve shown in brown on this diagram, and the height of the curve, how many molecules are there. And you note that as you go further to the right, we finally get some molecules escaping into the gas phase, and essentially what happens is those molecules escape and move on, that curve, brown curve and black curve, they start to decrease, and you have fewer molecules on that side. Eventually, all the molecules have escaped into the gas phase. So this is how we think about intermolecular forces and phase transitions. Okay? It involves the energy of the different states of matter. In this case, we only talk about solid, liquid, and gas. It involves that energy and how that energy is manifested, whether it's a solid, liquid, or gas, and what the intermolecular forces look like at each of these different phases and during transitions from one phase to another. So we've talked about these states of solid, liquid, and gas. Let's just take a closer look at the solid state of matter and the types of solids that we see and what the intermolecular forces might look like in solid states. Now, since we're talking about these solids, let's take a look at the solid states of matter, okay, and the types of solids that exist. One type of solid is a crystalline solid. The other is an amorphous solid. And then we like to talk about these solids as glass. So, a crystalline solid possesses rigid and long-range order. It's highly ordered. Crystalline is like your diamond. In a crystalline solid, atoms, molecules, or ions occupy very specific, predictable positions. Okay? A diamond is a diamond. You look under the microscope, you see it as a diamond. That's it. It has very ordered structure to it. All right? An amorphous solid does not possess a well-defined arrangement and a long-range molecular order. You don't know what you're going to get in the pattern of an amorphous solid. So be aware of that. Crystalline solids, by the way, tend to be more brittle. Amorphous solids tend to be a little bit tougher. Most of your glass in particularly homes are amorphous solids, just glass. It's not well ordered. It's not very crystalline. Okay? A glass is an optically transparent fusion product of inorganic materials that are cooled to a rapid state without crystallizing. In other words, we make the glass by solidifying it, but we don't allow it to form the crystal states. Okay? So let me say that again to be clear. A glass is an optical transparent fusion product of inorganic materials that have cooled to a rigid state without crystallizing. The glass gets hard, but it does not form crystals. It does not form a crystalline pattern. Okay? So be aware of that. We show you an example of crystalline quartz versus non-crystalline amorphous quartz glass. So we have quartz glass, and then we have crystalline quartz. All right? Now, solids will have a geometric structure to them. The geometric structure for solids is called a unit cell. A unit cell is the basic repeating structural unit of a crystalline solid. So if you have a crystalline solid, it will have a unit cell. It will have a well-defined unit cell. This means that essentially the crystal will form and it will replicate itself and keep replicating itself. It's like building towers, a skyscraper. It's basically replicated. Each floor for the most part is replicated until you get to the penthouse, of course. Okay? So that's what happens. A unit cell is defined and it replicates itself. And it has these lattice points. And at that lattice point, it can be atoms, molecules, or ions. But they will be well defined, and that's where they will be. And then within that unit cell, it will have these features that will allow you to further identify it based upon its geometry. And we're not going to go into the depth of this geometry, but we like to at least have you be familiar with. There's a geometry called a simple cubic, a body center cubic, and a face center cubic. And that helps you to understand where the points of location are within there. Face center is where the marbles would be, or body center, that's where the marble would be, or simple cubic would not have a marble in the middle of it. Okay? That is the extent of our discussion about the solid states of matter, and in particularly crystalline solids. So here's a summary slide of the types of crystals and their general properties. We have ionics, the forces that are holding the unit together, or electromagnetic attractions. They're hard, brittle, high melting, poor conductors of heat and electricity. And we show you some examples. Note these examples have elements from group 1 or group 2 with elements from the far right group 17 or a polyatomic. They're highly ionic. Covalent. The forces holding together are covalent bonds. They're hard, high melting point, poor conductors of heat and electricity. The examples of these are carbon, diamond, or quartz, or high purity silicon metal, which you find in your cell phones and other electronic devices. Okay? And then you have molecular. Okay? Molecular has dispersion forces, dipole forces, hydrogen bonds. Okay. These tend to be soft, low melting, poor conductors of heat and electricity. The examples we show you here: argon, carbon dioxide, iodine, water, carbohydrates, sugars. These would be molecular crystals. And then we have metallic crystals. They have metallic bonds. They're soft to hard, low to high melting points, good conductors of heat and electricity, which is why these metals are used. Okay? That's why they're used for electrical wirings. All metallic elements will fit this category, including sodium, magnesium, iron, and copper. So these are your types of crystals: your ionic, your covalent, molecular, and your metallics. There are different forces holding them together: electromagnetic for ionic, covalent for covalent, dispersion forces, which we talked a lot in this lecture, dipole, hydrogen bonding for molecular, and then metallic bonds. Metallic bonds differentiate themselves, or the metallic crystals differentiate themselves with their ability to conduct heat and electricity. Many of the others do not do so well at heat and electricity. The metallics are hard. Moleculars are soft. Covalents are hard. Ionics tend to be brittle. These are features you should be familiar with when you talk about ionic crystals. So, there you have it. Lecture 2 of Chapter 10 on intermolecular forces. That's Chapter 10, Lecture 2, Chem 111.